Hello friends, this is AKHILESH Pandeey, and in the last lecture we were discussing about the basic concept, and so I'll proceed with the same topic in the network analysis, and this is the lecture number 3 for the network analysis, and the chapter is basic concept. In the last two lectures we have studied charge, about current, about voltage, then after power, and then after we studied the classification of various elements. Okay, now this lecture in this lecture I'm going to introduce you about the three basic elements of the network, and these three basic elements will be very important throughout the network and throughout the network analysis. So study it carefully and note down the properties that I'm going to introduce you here, because these properties will be used throughout the network analysis. And the very first element that I'm going to introduce is the resistance. We all know about resistance, but for the exam point of view, the topics that are useful related to resistance are here now. First of all, resistance. What is resistance? So resistance is the property of an element that opposes the current flow. Okay, so if I am taking any conductor with some cross section, and through it if we try to flow some current, means by connecting some voltage or like that, means if I connect some voltage source across it and try to of course if we connect some voltage source, then definitely the current will try to flow through it, because there is a path for the current, and this is conductor, then it will surely try to flow the current. Now there will be a resistance to that flow of current, and that is electrical, means that is resistance, means resistance that opposes the flow of current. Okay, so here we learn that resistance is the property that opposes the flow of current. Now come to the derivation, the mathematical value of the resistance, and that is given by a very famous law, Ohm's law. And according to Ohm's law, we all know V proportional I, and it is derived as V equals to IR. In different books, it can be written as I proportional to V somehow. The same thing, both are the same things, but we generally apply a voltage. That's why we write it as a standard way, I proportional to V, means when we apply some voltage, because voltage we have, so proportional to that voltage, the current will flow. So that's why sometimes written in this way, but both are the correct. Both values are correct. Okay, V proportional to I or I proportional to V, whatever it is, but the final result is V equals to IR. And now we are here with R. R is resistance, and so we can define the resistance as V upon I. So there is a simple relation between voltage and current and the resistance, and that is R equals to V upon I, and the result is being denoted in ohm. So as per the law and the scientist name, and the resistance value will be valued in ohm. The unit of resistance is ohm. Now this is the basic introduction about resistance. Now if we take the cross section, and its resistivity, okay, the resistivity depends on the various elements, means if we are taking copper, then its resistivity will be different. If we are taking iron, then its resistivity will be different. So as per the element we are taking, the resistivity can vary, means it is material dependent. Now if there is a length L of the cross section conductor, cylindrical conductor, and if the cross sectional area is A, then the resistance defined for this element will be R equals to rho into L by A. Very useful formula, and sometimes the questions may be asked related to this topic, not directly actually, because this is very basic physics, but this formula is being used in so many other topics. Okay, so R equals to rho into L by A. Rho is the resistivity, L is the length of the conductor or the element, and A is the cross-sectional area. Okay, so we learned about resistance value, resistance relation with voltage current, and we learned about resistance relation with resistance for a conductor having cross-sectional area A and the length L and the resistivity of the material rho. So what about this Ohm's law? This Ohm's law, the condition for applying this Ohm's law or existence of this Ohm's law is temperature dependent. If the temperature is constant, then only this Ohm's law applies, otherwise Ohm's law doesn't apply. So what will be the value of the resistance? Means, of course, we have taken the resistance as a constant for this according to this Ohm's law, but resistance varies as per the temperature. So how it varies? Let's check it out. So the value of the resistance varies as per the temperature as R equals to R naught 1 plus alpha T. So T is the temperature, given temperature, alpha is the temperature coefficient for that material, okay, and R naught, of course, the temperature resistance value, resistance at 0 Kelvin, So this is the basic relation between resistance value and its resistance value at 0 Kelvin and the temperature. So we can see easily then that the temperature means it is a positive temperature coefficient. We can see that it is being added. So overall resistance increases when the temperature increases. So the metals generally have the positive temperature coefficient. It means that when temperature increases, the resistance value increases. This type of questions may be asked in the exam, and sometimes it has been asked in the engineering services exam. So how the metals, the resistance is being dependent on the temperature. So here we can see the relation easily. When the temperature increases, the resistance increases. So overall resistance having the positive temperature coefficient. This is about resistance. Now I come to the next topic, of course, related to resistance itself, and we will see that how the short circuit and what is the values for the resistance for short circuit and open circuit elements. Like we all just studied that if there is a conductor or there is a path, there is an element, whatever it is, I'm taking this as an element, okay, and so this opposes the flow of current. So sometimes it may oppose the flow of current with a very less value. So if the resistance value is very less, means roughly equals to 0, it means it is allowing the current easily to pass through it. If the resistance value is very large, means roughly equals to infinity, it means it is not allowing to flow of the current, means single current even cannot flow through it, okay. So it means overall we can see that if R equals to 0, it means the circuit is short circuited, means directly the current can flow very easily through it. So this is the case for the short circuit. And when there is an open path means it is not allowing single value of current through it, means current cannot flow through it, I equals to 0, then in that case, of course, resistance is very high, means infinite. So infinity means open circuit, 0 means short circuit. So for short circuit we can write R equals to 0, and for the open circuit we can write R equals to infinity. So this is the brief about the short circuit and open circuit resistance value. Now come to the next point, and that is related to the connection of resistance. And of course the connection can be in two ways. There can be a series connection and there can be a parallel connection. So if there is a series connection, let's take an example. This is R1, this is R2. So overall what will be the value of the current, the equivalent current? So here we can see that if this is the equivalent current, so R equivalent value will be R1 plus R2. So overall, if there is a resistance, if there is two or more resistance in series, then the equivalent resistance is given by summation of all these. Okay, it can be derived with the Ohm's law, but I am not going in the derivation. We just all know about this formula, so note it down. Next, come to the parallel connection of resistance. I am taking the only two values, R1 and R2. So if there is two resistance in parallel, then overall the equivalent resistance will be 1 by R equivalent, 1 by R1 plus 1 by R2. So this is the overall equivalent resistance in parallel, and this is the overall equivalent resistance in series. So this is the two connections that is being used, and on this sometimes questions can be asked in the exam, not directly in this way, in some other way it can be asked, and I am taking one of the example of those questions. Okay, so here I have one example related to the series and parallel connection, and it is like, let me draw the diagram of it first. Okay, so here we have that diagram, 2R, R, here R again and R, and so on. Means this type of pattern will be flawed. Okay, and now we have to determine R equivalent. I am not writing the complete theory in the question. Just diagrammatically we will understand this question, and the question was asked in 2014 2 marks question. It was 14 2 mark question it was, and the options were like this. Actually it was fill in the blanks type question, so there was no any option. 2014 2 mark question it was. R equivalent was asked for this question. Okay, R equivalent upon R, what will be the value of this? Okay, so here we have the question. First of all, we can see that this pattern will be like, if we take one R outside from it, then the pattern will be followed like R, 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 and so we can see that if we write in this way, I am taking one R, separate one R, so remaining one R will be here, R will be here, R will be here, again one R will be here, here R, here again an R, here again an R, here again an R, and so on. Okay, so what we have, we can see easily that if we take this part, okay, R and R, so this part is again repeated here, this part is again repeated here. So overall we can see that if we omit this part, even this part, then the remaining part will be similar like this one. Means we can see that either we are seeing from here, we are finding R up to infinity, or we are seeing from here again R up to infinity. So whatever the value from here, the same value will be from here, because the same situation is there. Okay, so if we consider one R dash, means equivalent resistance through this portion, then the same equivalent resistance we will get from this portion. Means if we take R dash as the equivalent resistance up to this point, okay, across it, and if we take R dash across it, then the question will remain same, because R up to infinity. Here again R up to infinity. Okay, fine. So R dash, I have not taken this one. R equivalent is here. Okay, I have not taken this one. I am starting from here itself. R dash, the arrangement will be R dash will be like this. This is R dash. Here we will have R, this R, and again this R I am writing. And for the remaining portion we can write R dash. For the remaining portion we can write R dash, because from here we can also see that R dash, overall equivalent resistance is R dash, so we are writing this. Okay, R dash and this R is in parallel, and that is in series with this R. So overall this R dash equivalent will be like this, R plus R in series with these two parallel combination, R parallel R dash. So R dash equals to R plus R into R dash divided by R plus R dash. So this is the derivation for this part, and r plus r dash. Okay, from this equation we will try to find the value of r dash. We will try to find the value of r dash. So how we can find it? We'll just try to solve it. Okay, I'm just going to solve r dash minus r. I will take here r dash minus r equals to r dash minus r equals to r into r dash divided by r plus r dash. So I'm multiplying it, and overall we will get r dash square minus r square equals to r into r dash. By solving it, we will get some value of r dash, and we will get some value of r dash, and that value will be added. That r dash value will be added with this resistance r, and so we will get the r equivalent, and then after we can solve it, r equivalent divided by r. So that is the simple calculation. So we can do it by using calculator or like that. Okay, so what we have to find? We have to find from r dash from here in terms of r, and that we will add with this r, and then we will get the r equivalent. R will be divided and the remaining value will be calculated easily. So this is the very basic funda related to the series and parallel connection of the resistance, and on this the questions can be asked in the exam. So that is mathematically somehow tedious at here, but it is simple, and only the logic is here given like this. Okay, so this is all about the resistance. Now I am coming to the next topic, and that is related to inductance. So here I am with that. Okay, so this is inductance. Again, just we studied that resistance is the property of the element to oppose the flow of current, and inductance is the property of an element to oppose the change in current. So it opposes the change in current, means any element. It is like this, means the circuit symbol for the inductance is like this, and it is nothing but the coil. Okay, number of coils is just like inductance, and its property is what? Its property to oppose the flow of current. Now come to the derivation of the inductance, and from Faraday's law we all know, we all know that E equals to minus d phi by dt for a single coil. If I am taking any coil and flux is passed, magnetic flux, of course, magnetic flux, we will learn it in detail in electromagnetic, but here we just have to understand that if magnetic flux is passed through it, and that magnetic flux is changing, means d phi upon dt, that magnetic flux is changing, then the coil experiences an EMF across it. The coil experiences an voltage, means EMF across it, electromagnetic force. This is equivalent to voltage, and that EMF is given as E equals to minus d phi upon dt, means change in magnetic flux equals to the voltage developed across the coil. This is for single coil. So if we take number of coils like this, then E equals to overall minus n d phi by dt. Okay, and we can write it as minus d f psi by dt. That is the total flux linkage, the change in total flux linkage. Now come to the point that the total flux for a current, for any current passing through it, passing through the coil, the total flux developed through the coil will be proportional to this I, means f psi will be proportional to this I. It means and this, when this proportionality constant is omitted and we take proportionality constant, and that constant is nothing but inductance. This L is inductance. So overall we get f psi equals to Li, means the flux passing, how much, means if the current is more, the flux linkage will be more. If the current is less, the flux linkage will be less. So overall the flux linkage will be proportional to I, the current, and so there will be a proportionality constant, and that is L, means inductance. So F psi equals to Li, and so we derive L equals to N phi upon I. N phi means N is number of turns of the coil and phi is the flux linkage through a single coil. So overall total flux linkage will be F psi. So F psi equals to N phi. Overall we got L equals to N phi upon I. Now here we can put F psi as Li, here we can put, so E equals to minus, or in terms of voltage we can write, instead of writing E we will write V, and I will omit the minus sign because it is just showing the direction, so no use of that in present situation. So I am taking only magnitude, I am interested to magnitude only. So d F psi equals to Li upon dt. Overall, just I told you that L is the constant, L is the proportionality constant, that is inductance. So L will be fixed for this element, and so we can take L out, and so we have di upon dt. So overall we have this formula, V equals to L di upon dt, and this is the relation between voltage and the current for any inductor. Voltage and current relation for an inductor is V equals to L di upon dt. So overall we have got this. Now the next point related to the inductance is its energy, the energy stored in an inductor. So we have V equals to L di by dt, and power, the power we know very well, V into I. We can write from here L di upon dt into I. Okay. And when we integrate the power, power is what? Power is the rate of doing work. P equals to dw upon dt. So if we integrate the power, we can get the energy stored in an inductor. Energy stored in an inductor. So integration of P dt. Integration of L di upon dt into I. In terms of dt will be integrated, dt cancelled out, we have L I di. Okay, L I di I square by 2, so we have half L I square. So this is the relation for the energy stored. This is the energy stored in an inductor. So this is an inductor with inductance L and the current I. Then the energy stored at any point will be half Li square, where I is the current flowing through it. So this is about the inductance. Now come to the very basic property of the inductance, means how it behave at the transient point and how it behave at the steady state point. So at transient point, inductance at transient point, transient means when there is some sudden change. So I have just told you that the property inductance is the that it opposes the change in current, means it doesn't allow the sudden change in current. It doesn't allow sudden change in current. Sudden change in current. Okay. Means there will be no change in current. Means if I am talking about t equals to 0 minus or t equals to 0 plus, like this, if I am talking about t equals to 0 minus, means before 0 second, if there is a current passing through it, flowing through it is 5 ampere, then at t equals to 0 plus, again that will be the same current, means I equals to 5 ampere, until unless any impulse function, means the infinite function signal is flowing through it. If that will be the case, then there may be some sudden change. Otherwise there is no sudden change allowed through any inductor. Okay, means whatever the value of this means just before 0 second, the same value will be there just after 0 second, and after some time it can increase only. At a certain point it is not going to change. Okay, so this is about the transient nature of the inductance. And what about the steady state nature? Steady state nature. So I am talking about steady state. Steady state means just establish the level where it is going to be stable. Okay, so I am talking about the inductor. Inductor opposes the change in flow of current. Means if I am trying to supply some value of current, means I am trying to attain some 5 ampere current through an inductor, so I will connect a voltage source through it, and that voltage source will try to change the current through it, and after some time I will reach to the point of 5 ampere. Then after there will be 5 ampere easily flowing through it. There will be no any change because I have got the stable state. So the current will become constant, and V equals to L di by dt, very well we know. So if the current will become constant, then the overall value will be 0, and so the voltage will become 0, means it will behave as the short circuit. Okay, so at a certain point when it goes to the stable state, there is no change in the current, so smoothly the current can pass through it, and there will be any no voltage across it, and V equals to 0, it means it will behave as a short circuit at steady state. It will behave as short circuit at steady state. So this is about the inductance and its some property. Now I am going to introduce you the connection of the inductance, and there can be of course the two types of connection, the series connection and the parallel connection. So this is L1 L2 and this is L1 L2. So in series the equivalent value is similar to the resistance L1 plus L2. L equivalent is L1 plus L2, and for parallel again similar to the resistance, and 1 by L equivalent will be equals to 1 by L1 plus 1 by L2. So this is all about the inductance, and this is all from this lecture as well. In the next class I will introduce the last remaining topic of the capacitance and some questions I will do, and that's all in this lecture. Thank you so much.